Hi, everyone. Our next speaker is Dr. Gavin McNicol, who is an assistant professor from University of Illinois, Chicago, and he will talk about emerging AI and ML applications in flux data processing.
Everyone. I know we're getting close to Jupiter and beer and pizza time, so thanks for your attention, and thank you for inviting me to give this talk. Yeah, I'm an assistant professor of climate and land surface processes at UIC, and just recently, with a little bit of a rebrand of my lab, also the PI of the Ecosystem and Planetary Health Integration Lab, which shortens to EcoFi Lab. And today, I think the goal is to talk about AI and ML as, I think, a bridge between today's session on data and moving into modeling. And I think from the last few years working on data-driven models, primarily and starting out as an empiricist, I do feel like it's helped me move into that modeling world. And hopefully some of this will help you as well. So the talk will cover kind of just thinking about that match between the strengths of AI and the challenges that we face as flux data scientists. Then we'll just talk briefly about AI mechanics, the kind of the heart of that machine. Some of that might be review for some people, but just I'm kind of trying out some teaching approaches here I use some of these slides for my teaching at school. So bear with me on that. You can give me feedback on it. Then I'll talk about an application to fluxes, so methane gap filling, and then talk about ways that we can bring some new directions within FluxNet, and then ways we can bring our knowledge as flux scientists to improve AI and ML. Yeah, why AI for flux data? And really, I think that the value of AI and ML is that it automates the identification of statistical associations in big data. So this lets us do the work that we like to do as scientists, looking at associations between data much faster and hopefully also more accurately, leading to better models. And increasingly, we can kind of open the black box of machine learning models, and we can increasingly use ancillary tools to describe and explain model behavior and learn something about the systems that we're studying. So maybe just to illustrate this point, as flux data scientists, we want to describe and explain and predict ecosystem processes. And so I'm going to show some methane flux data here from an upscaling project I was working on, where we trained a machine learning model to extrapolate from individual sites or networks of sites to the globe. And as a first thing, when we look at this as data scientists, we might see the seasonal pattern in methane indicated in these open circles. And we can describe that seasonality, the amplitude, the timing, and things like that. And then we might want to explain it and think about what's the association that seasonality has with some other driver. And so in this case, we might have a very simple model where we associate that with some function of temperature. And so we kind of move towards an explanatory phase. And then, of course, we want to predict. We want to go beyond our sites and predict eventually with our models. And so we might then apply our model in a new setting. So what we learned when we did this global scaling work was the way in which we describe and explain these multi-site patterns. But in this final panel at the bottom right, this is a tropical rainforest, this site in Peru, where the temperature methane associations that we trained our model on in the Northern Hemisphere primarily don't really apply, because it's always pretty warm in the humid tropics. And so the reason I'm showing this is that it's when we use these models for prediction, we also are doing hypothesis testing, where we can say, on the basis of this temperature model, does temperature drive methane flux variability in the tropics? And so it seems like, and that's actually a major area of new research now, is to understand wetland methane dynamics. So this is kind of what we do as flux scientists, going from descriptive to explanatory and predictive data. And I illustrated it with a simple example with monthly data, but as we've seen today, as members of the FluxNet community, we have access to hundreds of sites with half-hourly data, not just 4 sites with a few months of data. And so we are presented with this huge opportunity to learn something. but we also are presented with the challenge of working with this very big data, essentially. And so this is some data from a wet prairie that we set up a couple of years ago, flux site near Chicago. And you can see, just the richness of the temporal data for the NEE values at the top there, just for 2 years, and some really, patterns that are not immediately obvious for interpretation. And then you have all these ancillary variables, which in our case, we had a sensor array of 8 by 8, so 64 temperature and moisture sensors to interpret the fluxes. We wanted to do detailed work, but suddenly you have a high dimensional data set in this sort of generic data science lingo. We'd say it's high dimensionality, which means we have a lot of variables. And then for every year of observations, for each of those variables, we have like 17,000 half-hourly observations, right? So you have high dimensionality, lots of variables, and many observations. So we have big data. And then we're also getting this data from complex systems. So ecosystems are complex systems, and on the left, sorry, this is again, a timescale decomposed, a wavelet decomposed variability for methane fluxes from a wetland. And you can see that we have variance occurring at the seasonal timescale, then the multi-day kind of synoptic weather timescale, diurnal, and then even kind of an hourly timescale. And so even just for one of our time series, we have, and often the carbon fluxes that we want to interpret, we have layerings of signals that make it complicated to interpret just the initial measurements. And then, of course, we have nonlinear relationships. So methane and temperature has this more of an exponential response relationship. We also have lagged relationships between things like GPP and methane emissions. And these connections are up to other variables too. And then, of course, our data are also not perfect. So we have noise to deal with. And so if we have, big complex data sets, the take home here is that like this is the perfect data environment for artificial intelligence and machine learning. And given the limitations we all have as just one person sitting behind a desk. And so let's shift gears, and I hope it's clear that we have this opportunity to use AI to our benefit. And think a little bit about the mechanics of AI, and this might be a review. So essentially, AI is learning a multivariate association between conditions and an outcome. And it achieves that by iteratively training the model with examples and measuring the performance of the model against held out data. So sort of the core data science workflow of machine learning already embeds a component of model validation in a way that I think is beneficial for both empiricists and modelers to think about. And I'm at UAC, and there's quite a popular kind of basketball scene there. And so this is how I teach my students about some of the differences in the way that we can train AI and ML models. And so I've mostly worked with random forests, which I would think of as more of machine learning model. And but there's also kind of AI, and they're not entirely substitutable. So if we're thinking about maybe being able to predict the accuracy or success of scoring a basket, with the machine learning random forest, you can sort of think about, you might aggregate all the data for the last 10 years from the NBA. And then it's a matter of organization, of kind of splitting that data off into chunks of kind of similar conditions that lead to similar outcomes. And so eventually you might have this sort of map or tree, many trees of where you can summarize kind of the conditions under which you get a particular outcome, the conditions under which you can most often score a basket. But you don't really, there's nothing that's actually learned how to score a basket. It's just that you get an overview of the conditions that lead to that. Whereas with AI, I think I'm personally struggle to conceptualize sometimes the abstract ideas of the abstraction of neural networks. But essentially here you're training one by one the model to actually make that shot and measuring how far it is from the basket. And so the model actually learns how, in the same way that you might learn how to score a basket, but can't quite articulate in words how to do it. Right? That's why that's why I never learned how to be good at basketball, because I can't quite be trained that way. But yeah, so there's sort of this subtle difference, which I think I just wanted to illustrate, because it's surprising how, even though AI and deep neural networks are like definitely kind of, deep learning is definitely being picked up moving forward, it's amazing how some of these relatively simple random forest algorithms can actually perform very well and very quickly. So they're still being used. But across all of these different algorithms, the objective is to minimize the model error. And we sort of, the language around that is to minimize the cost function of the model. And so this model error is normally measured just as the mean absolute error, or the root mean squared error of kind of all of the observations and all of the predicted values. And so essentially, this process, we can leverage the fact that we can do rapid automation of this learning by considering a wide range of possible predictor combinations, and our second kind of tool in our toolbox is the fine-tuning, hyperparameter tuning that we can do of the model. And so we essentially have this whole landscape of potential conditions to explore, and leverage the fact that the machine learning model algorithm can quickly test out all of those conditions, and at the end we calculate our cost function, and we want to find the global minimum in this predictor tuning space. And so I think this is where sort of like the process model people and the hardcore empiricists, this is sort of the axis in which we can start to diverge from each other. I think, if you approach it truly as a non-domain data scientist, you just say, well, why don't we just try kind of anything that might be relevant as a predictive variable, so we kind of expand this space. And I think part of what we can do by bringing empiricists and process models together with this general workflow for machine learning is say, like, okay, well, what are actually the variables that are most likely to be predictive? So a lot of times it's a matter of we can just be more efficient if we can close that x-axis, and we can actually consider a more relevant range of predictors. So yeah, we have different algorithms to work with that kind of work in slightly different ways, but always we're trying to minimize the cost function. Okay, so then let's talk about applications to Flux data. So I'm going to talk about the one that is most relevant to data processing and that I know the most about, which is methane gap filling. And so really, this is an imputation problem. So the goal is to predict the missing values in a time series using a model. So this isn't interpolation, which would just be kind of fitting a linear model. We're going to use the information contained in the observations that we have to train a model that will then predict the values in the gaps. And the real take home here is just for F-methane from our FluxNet methane compilation, we now know that data coverage is not as good as it is for the carbon fluxes, other carbon fluxes, which themselves are pretty low. A good site might have 55%. This is US MIB. This is not far away in the California Delta. It's one of the best locations you could have for eddy covariance. You get this onshore wind every day developing in this like very consistent California climate, and even there you're getting like 40% data loss throughout the year. And then in places like in Alaska, you have months of no data, and then when you do have data, often it's still got a lot of gaps each day. So in this case, sorry, the black bars here indicate the percent data coverage per day. And what we don't have yet is the same standard gap filling procedure that we have for some of the other that have been implemented in these other data pipelines that we talked about today. So methane, we've still got some work to do. But what we tried to do is approach it in a kind of take the best practices from computer science and machine learning and AI and sort of map that onto this problem. And then we're now sort of trying to bring that back to apply to other workflows in Flux data. So the kind of the key elements of this, we wanted are to simulate, train, evaluate, and calibrate. And so those break down into, simulation is about making sure that when we need to create the conditions within our data that allow us to test the true predictive performance of the model when it's actually being used to actually fill gaps. real gaps. So in this case, I won't get into the details here, but in this case, we worked with these computer science students who were able to produce an algorithm that maintains the natural gap length distributions in the data. So when you're introducing all these gaps everywhere, it still looks like a methane flux data set. Then the next couple of slides, I'll just focus on the training and evaluation. And just to mention that, yeah, the calibration work at the end is also important, but I won't have time to cover that today. But essentially, the heart of it is in here that I'll focus on today, which is thinking about how do we prepare the data to train it? How do we construct model experiments by choosing different predictors and learner algorithms so that we can learn something about the best combinations of those? And then how can we evaluate those combinations? So yeah, I thought it would be useful to just kind of illustrate how this workflow works. So we have this is what we have to begin with, which is a time series with gaps in black. And the first step would be we want to create a test set. So we introduce artificial gaps that become the things that we can actually evaluate on. But for that first introduction of, in this case, we did about 10% of the data we introduced as gaps. That test set we want to set aside and not look at again until the very end of the process. It's important to not, we want an honest evaluation of the model performance. And the only way we can get that is if we set some data aside that we don't look at until the very end. We test on at the very end. So you generate this test set, set it aside, and then you want to set up, you want to iterate that process, generating another 10 versions of your test set data, and each time introducing another 10% of gaps. And so yeah, kind of the key kind of workflow element here is just to make sure that that test set gets set aside, and then to generate multiple validation sets. So these are the secondary artificial gap time series, so that we can train it for any given predictor algorithm combination. We can train an ensemble of 10 models, and it doesn't have to be 10, but you want to be able to capture the uncertainty within any given formulation. So this is kind of the generic workflow that we identified, and we think that it probably will transfer quite well across to other applications, maybe other fluxes. And then you can set this up in a way, if you're doing exploratory work to understand how well a given formulation might work across different sites, like we wanted to look at these 17 sites. You can set up experiments where you combine different learner algorithms with different sets of predictor variables. And so in our case, we generated 16 models from these 4 different algorithms, including random forest neural net. And then for the predictors, when it comes to methane gap filling, actually these temporal predictors are remarkably valuable, but they're basically just generic functions of sine and cosine for seasonality, and kind of a decimal day of year that allows you to find that unique location where you are in a year. But then we have MET, so shortwave in, temperature, pressure, wind speed, and then the combination of those two, or this baseline model. This is a model that Sarah Knox had used to initially test out some gap filling for methane. And the thing that we wanted to experimentally test was whether if we included additional variables, so if we just kind of threw everything that was measured at the site in, and in this case, these sites always included these soil measurements like soil temperature, soil water content, with these soil properties that, with these soil variables that are more proximate to the methane production, microbial methane production, would they help boost model performance? And so you can sort of set up, within this workflow, you can sort of set up experiments to look at mechanism. So yeah, our next step is then to do our model evaluation. So the metrics that we used for this were the R squared, which is really good for picking up that temporal association. So how good does it reproduce the seasonality or the diurnal pattern, for instance? The overall, in this case, we called it the normalized mean absolute error. So we looked at the mean absolute error across all data normalized by the variance at the site, so we could kind of get it onto the same axis, same scale, and then the bias, which is some closely related to the error. But essentially, our take homes from this, if we look at, we have the 4 different models, and then within each grouping, we have 4 different predictor combinations. We saw that random forest and XGBoost and ANN were kind of the best performing, but there was very little difference between XGBoost and on RF. So kind of these random forest algorithms were still doing well, even though they're kind of not strictly AI. And then the all predictors, when we added those soil predictors and everything that was at the site, actually, we were finding that was improving the performance just slightly. So if you look between the baseline in orange and then the green, there is some improvement there, both in the R squared and the errors. And then just to link back, because we've talked a bit about MDS, we did also apply the MDS gap filling approach that's used for CO2 to methane. And there is a consistency across all of these. We kind of talked about the fact that Gilberto earlier talked about the fact that MDS is sort of consistent and not easily displaced in gap filling because of its consistency. And so we sort of did see evidence of that across all these different predictor combinations. And there's kind of a narrower range of performance, which is interesting. But essentially, we did see improvement over MDS for the random forest and the ANN. Let's see, getting close. Okay, so I'm not going to spend much time on this slide other than to say that when it comes to model evaluation, it wasn't until I got into this kind of data-driven modeling world that I learned about Taylor diagrams and the way you can plot multiple performance metrics on the same plots, and it gives you an intuitive visual read evaluation of the model. And so the objective is to be as close to this little star here as possible. So any kind of Euclidean distance from this is a measure of the performance. And really here this was actually our final evaluation. So we took the RF random forest and the ANN, and we looked at how much the performance improved between the baseline and the all predictor data set. And you can sort of see this shift towards improved performance. So some of this was sort of just road mapping ways that we might recommend model evaluation work in other studies. And so, yeah, I sort of showed this piece here. We did also do some calibration work, which is really just about trying to address the bias that's introduced by doing AI and ML and recalibrate to the natural data conditions. And so there's some recommendations for that in the paper too. Okay, so future directions, I will be quick. Basically, take-home message is we can learn more about flux processes. We can improve flux data, as we've just talked about in the context of processing. And then we can also, I think, improve flux prediction models. Tammy's been working on this type of work, and I think others have here as well. So how do we bring knowledge and AI together? So the simplest, I think, the simplest kind of point I want to make is just that in the same study where we were looking at predictive performance, we also were able to query variable importance. And that's just that's a simple measure of how consequential a particular variable is on the predictions by the model. And this figure here really highlights that, we have soil temperature right up at the very top, which we were not previously including in the gap filling algorithms to train the gap filling models, but it actually popped out as being a very important predictor. It's not that surprising, really, in a sense that that's the point, is that like we can query and interpret the model structure and learn something about the drivers of the processes that we're predicting. And so now, like, it's not just random forests that you can do variable importance analysis on. There's increasingly sophisticated ways to get at what's driving the processes, what's driving the variance in your predictions. And so that's kind of falls under this variable importance box. So we can learn more about ecosystem processes. The second thing is we may be able to do a better job of data processing, like in this case, gap filling. And so Sarah Knox, myself, Kyle Delwish, and Jiangmin Sun are leading a working group under the FluxNet co-op umbrella. And you're very welcome to join if you're interested. We've talked a lot about methane and not much about nitrous oxide. So if N2O or CO2 is interesting to you, actually, like, taking what we've learned and what we're trying to establish as processing guidelines for methane and applying that to N2O or CO2 could be something that we could develop in this group. And so last fall, we had a workshop where we were kind of trying to distill out some take-home messages that we could use to incorporate new gap-filling approaches into OneFlux. And so Sarah Knox is currently kind of working with Euroflux and Ameriflux to incorporate some of what we've learned. So they're trying to explore, what are the best predictors and models, like learner algorithms that would actually work well across all of the FluxNet data sites. And so Gilberto was mentioning earlier that challenge of like, how do you make a workflow that works across 100 and 500 sites or something. And then in addition to calibrating uncertainty, which we've been working on, we also want to look at the error terms in our flux estimations as well. So there's sort of a relationship there where we're exploring whether our uncertainty estimates from the gap filling process can be used as a measure of random uncertainty. But essentially, in the next year or so, there should be clearer community standards articulated around how we can gap fill methane and get good methane data. And then the very last point, thank you for giving me extra 5 minutes, is that there's also just this explosion of possibility with this knowledge-guided machine learning. So, the purely data-driven work, we can go faster and we can do things faster and sometimes more accurately. And sometimes we can query to learn something about processes. But really, if we more deeply integrate what we can do and know as flux scientists with AI, or what we know as process modelers with AI, we can move from what are essentially trial and error models where, we're throwing the entire kitchen sink as variables in and just getting the algorithms to search across this vast predictor space and try to come up with something that looks good, to maybe following rules or recipes or observing the chef to get towards truly knowledge-guided ML. And so, like in the case of observing the chef, we're thinking about taking the idea there is called pre-training, and so you take the output of a process model, which is the predictions inherently reflect the relationships between, say, temperature and methane or other fluxes that are embedded in what we already understand, and get the AI model to learn those first and then be fine-tuned on the real data. And maybe we could encode a recipe. We could say that, okay, methane flux is always downstream of carbon being in the soil. There's no carbon in the soil, you're not getting any methane. Or if there's no GPP, there's no methane. So there's sort of a sequential information that you could build in, or you could apply general rules like catalytic processes always accelerate under warmer temperatures. And so we can kind of move towards like a better robot cooking our dinner, essentially. So yeah, I think conclusions are, I think I'm excited about the next 2 days because I think we'll be thinking about how data and models are coming together, and we're at a point where I think we're at a great point for integrating ecosystem knowledge with AI and ML. Yeah, I think I left kind of here with the future is here, and I think like actually, I mean that as in like the people in the room. I think, yeah, if you're here and you're interested in this topic, then you will be driving these questions forward. And then, yeah, that's the code base for the gap filling workflow. And if you want to join the committee, just shoot me an email. Thanks.
So for until data gap filling is even more difficult compared to methane, do you think it's the same kind of quality level?
Yeah, I don't know that I could make a general comment there because I don't think we have there's not a whole lot of eddy covariance in N2O yet. But I think, I mean, in some sense, it's even more ephemeral because I feel like you have, if you get reducing conditions in a wetland, you eventually get methane and it kind of bounces around, but there's still a source. Whereas in N2O, it's often like a pulse. So like you'll have this baseline of, so I think one thing people looked at is like whether you need to sort of kind of do like a sort of an event-based model where you're trying to predict something during a period where you're getting fertilizer applied or you're going through some other transition. And whereas with methane in wetlands, we've sort of had this, it's more of like a constant source to some degree. So I think short answer is it'll be hard. It'll be even harder, but a really cool thing to explore that I don't think has been touched on really. So.
Slides, you showed the performance of using a relationship between methane and temperature versus observations, and how you have 3 sites from the US and 1 from Peru. Were the predictions in that slide, were they from your gap filling technique, or was that a different model? And do you, like, are you seeing that sort of site level variation from your gap filling technique as well?
Yeah, so that, you know, the 2 kind of AI or data-driven work projects that I've done are gap filling and then a sort of global extrapolation from the FluxNet methane network. So that project was, that those first figures was from the upscaling work. But it was still, I think that's one thing I wanted to convey actually that I didn't quite put into the talk, which is like just the way that once you start thinking about these as workflows, modular workflows where you're swapping in and out elements, it doesn't take a lot to go from to go between upscaling and imputation, you know, and there's a lot of take homes and best practices that apply to both. So yes, that one was from the upscaling project. And so yeah, we saw sites where mostly in the tropics where like our predictions were really not great, even though we were training with some tropical data. It seems like hydrological dynamics are perhaps more important than just temperature changes in some of the tropics. And then for the performance across sites and the gap filling, I don't know if you remember, but there was a couple of sites there. It didn't matter what we threw at it, like the predicted performance on the R-squared and the errors were poor. And so I think you get into that question of like what predictability at sites. And for instance, one of those 2 sites is this site in Alaska where the fluxes are very low all year round. And so when you have a relatively noisy methane signal, your signal to noise ratio is just poor. And so getting a good R-squared is like unlikely when you're trying to get that half-hourly bounciness right. So yeah, short answer is there's a big spread across sites.
I do have a question related to this slide. So I know in statistical model, we do have this overfitting issue. I saw that your baseline model and all prediction model actually does not differ from each other that much. So does the all model has issue of overfitting? Yeah,
so if you're giving it a lot more variables to work with, you might just be overfitting. Yeah, that's I think that's a totally valid point and something we're definitely concerned with. I think in this case, looking at this figure, what I'm seeing is like there may be a tiny difference here. It's explaining like whether or not this gets captured by the whisker or not. And so I don't think it applies in the comparison between the baseline and the all. I think it could be a reason why we're getting a slight improvement in the model performance, but we did try to set up the workflow and do everything we could to mitigate overfitting. And so the measure here, I think that maybe the final test so this was on the validation set. So you're looking at the performance across those 10 initial models that you trained. And then we took the RF and the ANN, and we then tested that against the completely held our test data. And we still did see quite a bit of improvement. And that would be like probably our main step to assess overfitting would be if the kind of improvements maybe disappeared here, or we're getting very different results when we look at the test data. So I think it's a really important point. It's like, how can you avoid the overfitting? And one of those best practices is actually keeping the dimensionality of the predictors low.
That like from the action we had many measurements, and so how the minimum to take the minimum number of samples the net and the correlation between the.
Yeah, so basically we had this threshold of about 12 days. I'm trying to remember if that was based on past literature or whether it was something in our data. But basically we did distinguish when it was a really long gap like this, like 6-month gap in this Arctic site. And in that case, we recommend in the paper like not people not to use this workflow to fill that gaps that are that long. But I think someone earlier today was talking, forget who was presenting, but they were talking about a ML algorithm that was being used and was robustly filling long gaps. So I was wanting to talk to them. But yeah, so that we kind of made some recommendations about like depending on how long the gap is, you may or may not want to use this workflow. But the threshold we used was I think it was this 12-day threshold that there had to be an observation, at least one observation within that 12-day period. And yeah, and then so we can for these sections here, we'd recommend it, but you would exclude the long gaps.
So in the difference between the schools and rainforest and
Only this one. Oh, I'm sorry. Yeah, I think I was pointing to the wrong one. So yeah, these are the two like random forest algorithms in the necessary ANN. So there was a bit of a step change here. I was pointing to the wrong one before. There was a bigger difference between ANN and RF than between the two random forest like. But I think in other papers I've seen activists do quite a bit better than random forest. So it's probably recommended in a lot of cases.
and oh, so you find that soil temperature is very important variable for the idea capability. And then what your which layer for temperature. That what we soil if soil.
Yeah, we limited it to surface, like the shallowest readings about 10-15 centimeters, I think.
And the layer is nothing for us to 2.5 or
Yeah, we tried to we identified those 17 sites for the consistency and the predictors. So I think it was always like a 15 centimeter measurement.
Gavin's gonna join for dinner.
Yes, yeah.
He's like,
Thanks. Appreciate it.
Yeah, thanks everyone for the lively discussions and being like creating such a welcoming space for all of the Neanderthal voices. Yeah, so just a reminder for tomorrow, we're gonna need the Docker installed in all of your machines. So you can do that for the 2 tutorials. Also, we're meeting back here starting again at 9 a.m. But for tonight, here's a informal social dinner. It'll be in Jupiter, 5-minute walk away, just across the street from here. Out, turn right, and then left. Yeah, or plug. Yeah.
that's at 6 p.m.
That's at 6.
So for Docker, don't install it tomorrow here because the internet is slow. It's gonna take forever. So it's like we recommend to do it like not here before tomorrow. So it's like downloading 2 gigabytes. So it needs some internet. So if you want to do it like tonight or tomorrow morning, you can do so. And if you have any questions, you can ask me or Katie about the Docker installation.
So we'll be here for the next time.
Yeah.
So if you did run into issues with Docker and you need some help, we'll be hanging out for a half hour. Come see us and we'll figure it out.
Thanks everyone. Yes. Yes, you're so Docker is creating a version. Yeah.
Thank you. Thanks.
Can also be used.
Yeah. So let's. I think the image is nice. They go. Yeah, that's the, yeah.
Yeah, that's the one.
for reading the
Yeah.
the Jupyter one is like 5. So you need 20, let's say that's like something easy. You can still use your computer.